All right, our next question is a really good exercise and something that we'll have to get used to. It's messy, the notation is cumbersome, but let's get ready for the big stuff. We'll see it again in several other classes, especially if you're a relativity fan. You got to get used to this tensor notation in dealing with them. All right, so the statement reads, consider an infinite parallel plate capacitor with lower plate at Z equal to negative D over 2, carrying surface charge density negative sigma, and upper plate at Z equal positive D over 2, carrying charge density plus sigma. A. Determine all 9 elements of the stress tensor in the region between the plates. Display your answer as a 3x3 matrix. B. Use a static force equation to determine the electromagnetic force per unit area on the top plate. All right. C. What is the electromagnetic momentum per unit area per unit time crossing the XY plane or any other plane parallel to that one between the planes? D. Of course, there must be a mechanical force holding the plates apart. Perhaps the capacitor is filled with an insulating material under pressure. Suppose we suddenly remove the insulator and the momentum flux C is now absorbed in the plates and they begin to move. Find the momentum per unit time delivered to the top plate, which is, say, the force acting on it, and compare your answer to part B. All right, sounds pretty cool. Let's get ready. All right, so for part A, the electric field of a parallel plate capacitor is E equals sigma over epsilon naught in the negative z hat direction. Or write it in the angle bracket notation. We see that we have 0 in the x hat, 0 in the y hat, and negative sigma over epsilon naught, okay, for the z hat. So this this is a static field, so there is no magnetic component. Okay, so we see here that if we just break this down, we see from the definition of the stress tensor, we have exx minus the delta term, xx. Anywhere we have an x and x, the delta goes to 1. If it's xy, it goes to 0, and you can see everything follow through like that. So really what we're looking at is the diagonal terms are staying intact, with the x component and the y component being 0. A lot of the stuff is going to cancel, so just let the math take its way through. If we plug this into a matrix notation, what we see here is that we have epsilon, and then we have ex times ex squared, or ex times ex, which is ex squared, but again it's 0. And then we have e field squared with the 1/2. So if you notice on the main diagonal, we have the minus 1/2 e squared on all of them. And then you go to the z on the main diagonal, that's the only one with an ez squared, because that's the only component that we have. And then you see every other one that's off diagonal is multiplied by a 0 component, so everything off diagonal goes to 0. What a wonderful surprise. Okay, so if we go ahead and simplify this and we factor out an epsilon, you see that the main diagonal is composed of negative 1/2 e squared, negative 1/2 e squared, ez squared minus 1/2 ez squared, since again the e field is only in the ez direction. So what we do there is we just substitute it in so we can solve for the plus on the zz component. And yeah, as you see here, everything else would be the same thing. So we just factor out a e squared and a 1/2. And we're left with the negative 1, positive 1 on the main diagonal. And so if we plug in what e is, that's negative sigma over epsilon squared. A factor of epsilon will cancel, and we're left with sigma squared. The negatives clearly cancel. And then we have a factor of 2 from the 1/2 and epsilon naught from the square. And then again, main diagonal, negative 1, and positive 1. That's not too bad. All right, now for part B, since B is 0, the pointing vector is 0, since E cross B, which would be E cross 0, is all 0. All right, nice there. Thus, we need to integrate over the xy plane where the field is. So dA is equal to negative dx dy, again, due to where the positive and minus charges are. Pretty good, and what plate we're looking for. Okay, so the force is going to be downward since we're positive up top, negative on the bottom, I believe. Yeah, and so we're looking for the force on the top plate. Let geometry speak for it. So FZ here is equal to TZZ dAZ. Again, since we don't have anything else to do with the X or Y direction, the only direction that the field travels now is in the Z direction. So that's only one that can carry force. So let's get that through. Once we do this, we know that we're going from negative Y to Y, negative X to X, because we're looking at an area. Okay, so let's shove everything through. Our E field or TZZ component there is this positive 1 times the constants, and since they're constant, they can be moved outside the integral. And then we use Fubini to split the integral up. And we see that we end up with the negative sigma squared over 2 epsilon dy dx, which again we'll just label as A. So the parallel plate area. And then, once we do that, we can solve for the force per unit area by dividing this F by A, so the A's cancel. And we see that we get negative sigma squared over 2 epsilon in the z-hat direction, as expected. All right. That's exactly why we use the A notation, cancel them out. All right. So C, the momentum crossing a surface perpendicular to the Z per unit area per unit time is negative TZZ. Okay, so as we see, the force above is negative. So crossing perpendicular to the Z, we see that TZ component needs to be negative to counteract that. So hence the negative sigma squared 2 epsilon naught. The recoil force, again equal and opposite, delivered per unit time to the top plate is F is equal to negative sigma squared 2 epsilon naught. So again, we're all looking the same, and we have several ways to get there. There is a couple more things to note, but I'll put that in the description. And yeah, let's have a discussion.